This is Calc 4, Lecture 18, Linear Algebra. That is the Chapter 4, General Vector Spaces and Subspaces. Okay, we say that a subset W of a vector space V is a subspace of V if it is a vector space on its own. Now, I didn't add that it should be a vector space with vector addition and scalar multiplication that it inherits from V as a subspace, as a subset of V. Then there is this important theorem which says that W is a subspace of V if it is closed under vector addition and scalar multiplication that it inherits from V. And that's all. Remember, to be a vector space, there were like several axioms, and a set with two operations defined has to satisfy those axioms to be a vector space. But this theorem says no, it's just enough to check and see if it is closed under these two operations. Now, all those axioms, if you look at them, are satisfied, except we should check two of them. And I remember yesterday I said that this axiom about the zero element is crucial. So let's see if this zero element is here. Now the zero element, if some, well, this W is not empty, so there is at least one, say, a vector in this subset. So let's assume that it's not empty. Then 0 scalar times U is 0 vector. Since it is closed under scalar multiplication, so this scalar times this vector, which gives me a vector, is in W. Therefore, 0 is in W. Second, we have to check something else, that negative of any vector in W is also in W. Okay, what is negative of U? Negative 1 scalar times vector gives me negative U. So scalar times vector is in W. So negative U is also in W. Therefore, W is a vector space with those two operations from V. Well, since we will be dealing with the subspaces a lot, that's all you have to check. But there's another thing that comes in, and that's even easier when we want to prove that something is a subspace. There is something else that if we check, then it is simply a subspace. We don't have to go through these two. Okay, so let me give you examples of subspaces. So let's take R2, R2. So R2 is a plane, XY plane. Now any line that passes through 0, 0 is a subspace. Any line that passes through 0, 0 is a subspace. Now, what is the equation of a line? So, if this is L, what L is if it passes through point 0, 0, it is like this. So, L is something like we can write a vector form of that. The vector form is K times V for some V. If this is V. So that is in fact K times V for K, a real number, right? So that V is the direction of that line. So this subset of R2 is a subspace. Now you can just check two things. I'm not going to check that, so you can check it yourself. But you might ask, or you might wonder, why, say, this line, for example, is not a subspace. this line L, say L prime something. Well, this line L prime is like this. Remember, if L prime is something like this, it's like m sine times some u, say a vector like this, plus some b, right? Or, well, we usually write it as x0, so then we write x0 not b, so you get confused with something else. So x0. Okay? So x0 might be a point here. Okay? And m belongs to R. Just look. Is 0 in this set, 0 as a vector is not in L prime. And you can see from the picture. Why? If m changes, there's no way that you get 0 here. No way you get 0 here. So 0 is not in this subset. Therefore, L prime is not a vector subspace. L prime is not a subspace. Well, L prime is a different kind of subspace, but I'm not going to confuse you. But anyway, so, and you see, I just checked one thing, 0. I just asked, is 0 in this subset? No, it's not. So this is not a subspace. This one is a subspace, this is not a subspace. Another subspace is, in fact, the 0 subspace. The 0 subspace is simply this. Well, if you're, let me remind you what 0 is. 0 is in fact 0, 0. 0 vector is 0, 0. So that by default is a subspace. It just satisfies everything. In fact, 0 is a subspace of any vector space. I mean, 0 of that vector space. Now R3. So let's look at R3 and see what we have in R3. In R3, any plane P, planes that pass through 0, 0, 0, 0, 0, 0. Okay, so these are they are like something like this. They are like, say, T, U plus S, V, remember? And T and S belong to R. So that was like the vector equation of a plane that passes through the origin, 0, 0, 0. Well, I don't know if I can draw a picture of this specific one that goes through 0, 0, 0. Let me try. So, oh, this is not a good one, so let me make it kind of crooked. So this might be a plane that goes through 0, 0, 0, and okay, so let's see if that is, well, we can see all of them, say. Okay. So it's like this, and this. So it's, gee, I can't show you something. But anyway, so this passes through 0, 0, 0. It's not easy to draw a plane that passes through a certain point. Like that, in fact. Okay, so, but what about other planes that do not pass? They are not vector spaces. They are not, say, subspace. In fact, they are not vector spaces, so they are not subspaces. So that is one. The second one is lines that pass through 0, 0, 0. So these lines are like lines in dimension 1, R2, and K belongs to R. Okay? And the third one is the 0 subspace. The zero subspace. So basically for R3 we have three types. One type is planes that pass through the origin. They are subsets like this, generated by two vectors, u and v, and they are lines that pass through 0, 0, 0, and they are generated by one vector, and the zero subspace, which, as I said, the zero subspace is always there. Okay. So let's look at subspaces of other vector spaces that we studied yesterday. So say let's take M, say 2 by 2. Remember that was matrices like this. Okay, these are matrices like this, and what is a vector subspace of this? Well, one of them can be this. Let me. So W can be a vector subspace like this. A11, A12, 0, A22, and Aij belongs to. So this means that all 2 by 2 matrices such that this is 0. A21 is 0. So all of them have 0 here. All of them have 0 here. Now let's check. Now how do you check this thing? First of all, if I add 2 vectors or 2 matrices like this, I should get another matrix with the same property. You see, you can write this property here. You can write, this is a set of 2 by 2 matrices such that N321 is 0. N321 is 0. So you can write down so I can say this is let me write it in fact, that's good. The set of 2 by 2 matrices with A21 equal to 0. In plain English language, that is set of 2 by 2 matrices with A21 equal to 0. So let's check. Let's take 2 of them, A11, A12, 0, A22, plus B11, B12, 0, B22. So I will get this, A11 plus B11, A12 plus B12, 0, 0 plus 0 is 0, A22 plus B22. So let's see. Does this satisfy the condition of this set? Yes, because A21, or let's say this N321, is not necessarily N. So I should have said N321. N321, not A21. Can you say what is A? So N3 will N321 equal to 0. So this is N321, and this N321 is 0. Therefore, this belongs to W. This matrix belongs to W. So this is closed under addition. Under addition defined here. Remember, addition in this vector space is simply adding matrices. So it is closed under vector addition. Let's check the other one. Scalar multiplication. So let me erase this and multiply this by some scalar, some k. So this will give me k, A11 k, A12 0, k, A, 2, 2. Look at this. This is a matrix with entry 2, 1 equal to 0. So this belongs to W. Therefore, it is closed under scalar multiplication. So this subset is a subvector or subspace of M2 by 2. In fact, if you choose more zeros here, just set some of them to be 0, that is also a subspace. Now you might ask, what if I choose 1 here instead of 0? So let's see. Let me erase this, and that's like another. Let me use something as W and say, I don't know, like W prime, say something. Then let's put just 1 here. And it is that this is 1. Entry to 1 is 1, not 0. Why this is not a vector space? You don't have to check those two. Remember, I told you to check and see if something is a vector space subset. The best thing is to look at that axiom about the 0 element. Ask yourself, does this include the 0 element? Is the 0 element an element of this subset? The answer is no. No 0 element. Why? But you can put 0 here, 0 here, 0 here, but this is 1. You can't change this. This is 1. No 0 element. This is not a 0 element. Not a 0 element. No element can be 0 element. What is 0 element? 0 element is an element so that you add to anything, you don't change it. So if I add it to something, it shouldn't change it. But if I add it to this 1 plus this 1 will give me 2. So entry 2, 1 will be 2. It has changed. But anyway, you can also use, you can also show that when you add 2 of them, you will get a 2 here, and that is not an element in W prime. So this is not a vector subspace, or a vector subspace. So no 0 element, and this implies that the W prime is not a subspace. But it's better to say vector subspace, because this is another kind of subspace, but I just write subspace because I didn't discuss anything else. Okay, so if I am given n by n, any matrices, m by n matrices, that is again the case. If I set some of them to 0, some entries to 0, that is a subspace. So subspaces of n by n are includes matrices with certain entries equal to 0. Well, there are other subspaces, but those are the ones that we will see what they are. So this will say polynomials. Let's take P, say 5. P5 is A0 plus A1x plus A2x2 plus A3x3 plus A4x4 plus A5x5. I's are real numbers. If I look at this, if I set A4 and A5 to be 0 all the time, so if I set A4 and A5 to be 0 all the time, then I have this thing, something. It is this. Zero x4 plus 0 x5. Okay, if this is the case, then what is this? 0, 0, nothing. So this is in fact P3. This is P3. And it's very easy to check that, in fact, this is a subspace. So P3x is a subspace of P5x. Well, when I write this thing, this means subset. But I should write somewhere that it is subspace, in fact, not just subset. So this is a subspace. In fact, P1, P2, P3, P4 are all subspaces, and it's interesting. The vector space is a subspace of itself. Sometimes that is useful to understand that a vector space is a subspace of itself. Okay, so that's like the whole thing. Well, it's okay. We can also say that. Anyway, so for polynomial spaces or PIs, PN, say PNXs, all PIXs for I less than or equal to N are subspaces of this. Okay, let's go to function spaces. Function spaces, so I said the F, let's take function spaces defined on some, in fact I think in the book it is from -infinity to infinity. So these are all functions defined on R to R. In fact you can write R here, but this is the whole R. So let's take continuous functions. Continuous functions are f's such that f is from R to R and it is continuous. Okay? Let's take differentiable functions, one-time differentiable. F is from R to R and f is differentiable. And you can just go on, and you might have negative infinity. Infinity is the functions from R to R, such that f is n times differentiable. Okay, and this goes on and on until you reach C infinity. C infinity minus infinity, infinity, and that is if they are what we call smooth. So these are like infinitely many times differential. So they are infinitely many times differential. Okay, now what are so examples of this one? As I said, examples of this one is this: absolute value of x. Absolute value of x is continuous, but absolute value of x is not differentiable. Okay, differentiable implies continuity. This implies this. This implies this. From Calc 1, I guess we prove in Calc 1 that if some function is differentiable, then it is continuous. But if it is continuous, it doesn't have to be differentiable. And this absolute value of x is definitely a good example. It is not differentiable at point 0, right? Remember x, y, and this is the graph of absolute value. It is not differentiable here. So absolute value of x is not differentiable, and so on. Now, what are examples of functions that are infinitely many times differentiable? E to power x, sine x, cosine x, right? And you can also say any, say Taylor series. Just write a Taylor series with some coefficients. That is also infinitely differentiable. So the thing is that each one of them, if you recall from Calc 2, each one of them has a Taylor expansion about 0. And the Taylor expansion is, if you look at it carefully, that is a polynomial of degree infinity. E to power x has x, x squared, x3, x4, x, all x's to any power. So you can say that these are like polynomials of degree infinity. So this guy here, in fact, includes any polynomial of any degree. Any polynomial of any degree. Although, if you differentiate a polynomial of any degree, at some point you will get 0. Because the polynomial just reduces each time you differentiate a polynomial, it reduces its degree, it reduces by 1, and at some point it is 0. So we can put all these things in a picture, all these function spaces, and so these function spaces are like this. So if I have all function spaces, this is the set of all function spaces, so this is like F, infinity, infinity. Then inside this we have C1, C1, then inside this we have like C2, and it goes on and on until we have, say, C infinity, and inside this we have polynomials of degree n. Okay, so, and say if I have polynomial degree, say 100 here, polynomial degree 99 is inside, so it just goes inside, move, 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 until it reaches 0 polynomial, say. So this is like the largest one. Any function, not any function, is what did I write this here? So this is C, this is C1. Sorry. So not any function is continuous, and not any function is differentiable, and so on. Okay. So this is these are some examples, important examples of subspaces of some vector spaces that I discussed before. Okay, let me see what else is in this section. So I discussed that. Can't remember what. I discussed the definition of okay. Important definition. Linear combination. So, given a set of vectors, say u1, u2, say in V, a linear combination of ui's is some u, which is k1, u1, k2, u2, km, and ki's are scalars. Ki's are scalars, they belong to all. Okay, so a linear combination is simply some scalar times the first one plus another scalar, or some scalar times the second one, and go and so on, up to the last one. Now, all of them can be 0. So, or some of them can be 0, or something like that. So, they are just scalars, any real number. Okay, so why is it important? Let's look at certain things. You see, when we define something, I usually go back to, say, systems of equations. First of all, before talking about system of equations, if I have, say, a vector in R3, let's go back to physics. Usually they write vectors in this form. They say 3i minus 5j plus say 6k, right? So we can say that this u is a linear combination. The linear combination of I, j, and k. Right? We can say that the u is a linear combination of I, j, k. Back to systems of equations. System of equations. So if I have, say, a x equals b, say, let's say that a is m by n, and then x should be n by 1, and this should be n by n. So b is n by 1, right? So this one has a column 1, say, column 2 up to column number n, right? That is a. And x is simply this, x1, x2, up to xn, right? And this one is b1 up to bn. Okay. Now when we look at this, I will write down the system again right here and show you. But when you expand this and write it as a system of equations and then come back to vectors again, this looks like this. It looks like x1, or let me put vector here because in fact these are columns as vectors. So it is x1 column 1 plus x2 times column number 2 up to xn times column number n, and this equals this vector, b1 up to bn. So I turned a system of equations into this interesting equation. This looks like one equation. So this equation is this. So this is equivalent to asking this, this question. Find xi's such that x1, c1, blah, blah, blah equals this. So this linear combination equals some vector b. Okay, so this comes down or can be interpreted as this kind of equation, a linear combination, say, equation. So you see the columns of this are given. A is given. So these columns are given, these vectors are given. So we are asking for what values of x when you add these columns, like saying these columns are like this. So the columns, if we're in R3, they're like vectors like this. C1, say, C2, and C3, say, right? And this B will be something like this B. We are asking what fraction of this plus what fraction of this plus what fraction of this will add up to give me this, right? So it's like saying, okay, C1 times X1 is this, X1, C1, then I add it to X2, C2, and I add it to X, say 3, C3, and I end up, let me draw, and I end up with a vector like this, and this should equal to my B. You see? So some fraction of C1 plus some fraction of C2 plus some fraction of C3 add up to B. So you see this system of equations comes down to like this picture in R3 or in any Rn. You can just draw a picture like this. That you are given like three vectors, at least this is like the three equations and three unknowns. You are given these three vectors, and the question is for what values x1, x2, x3 as scalars, when I multiply this by x1, this one by x2, this one by x3, and add them, I will get B. So the system of equations is interpreted in this way as a problem on, say, linear combination. Now, you might say, how did this happen? Let me... So that AX equals B is in fact like this. That was A11 x1 plus A12 x2 up to A1n xn, and that is B1. A21 x1 up to A2n xn is B2. AM1 x1, AM2 x2, AMN xn is Bm, right? Look at this, not this way, this way. Let's look at them column-wise. So look at this column-wise, this column here. This column is like x1 is multiplied by what? That is equivalent to saying x1 is multiplied by A11, A21 up to AN1, right? Then the second column is x2 multiplied by A12, A22 up to N2. And this continues to x, what's the last one? Xn multiplied by A1n, A2n up to Amn. And that equals B. Okay? So this is column 1, this is column 2, and up to column number n. So that's how you can write this as a linear combination of its columns. So AX is a linear combination of the columns of A. So AX is a linear combination of columns of A. We will see what columns of A, when you put them together, it's called the column space, and so we are in fact trying to find a vector in the column space that equals B. So we will see another interpretation when we discuss column spaces and row spaces and other things in this chapter, in fact. So that is the story of linear combination. I guess there is also another nice another important definition is this important definition. Well, if I have that is definition of span. Okay, so linear combination and span are related to each other. So let's take some vectors. So let's say say S is, let's say, ui, u2 up to un, and it is a subset of V, then span of S is all linear combinations of S. So all linear combinations of S. What does it look like? It is something like this. K1 U1 plus K2 U2 plus Km Um, and the Ki's are scalars. Ki's are scalars. So all linear combinations of elements of the subset. So that is called span of S. Span of S. Now, it's not hard to show that span of S is in fact a subspace of V. Span of S is a subspace of V. Important. It's not hard to show. In fact, you can show that easily by just proving those two conditions. But this is another important theorem. And I put so many stars because we'll be using this a lot. And let's see. And given S U1 up to UM, then span of S, which is again in V, is a subspace of V. We will see that if I have a finite dimensional vector space, then any subspace is like should be span of something, which those vectors are called like basis for that subspace. We will see what basis is, and so that's why this span is like universal. Now, let me give you an example of span. Okay, let me erase this thing. Example. So let me write this system of equations: x1 plus 2x3 minus 5x4 equals 0. Then let's write x2 minus 10x3 plus 12x4 is also 0. Well, this is in fact 1, 0, 2, -5, 0, 1, -10, and 12. You see, this is in RREF form. It is RREF. So we don't have to reduce it. So this is reduced. So we need two parameters. So let's say x3 is R and x4 is T. Then I have x1 equals minus 2R plus 5T. x2 will be minus 10 as 10, R minus 12T. And x3 is R, x4 is S. Okay? No, RT, sorry. R and T. So I can write this in vector form. Vector form is x1, x2, x3, x4. And one thing, when you're writing this, don't forget these two. Don't just write the first two or the ones that are calculated or written in terms of the rest. No, write all of them. So this will be r times minus 2, 10, 1, 0 plus t times 5 minus 12, 0 and 1. Okay? So what can I say? This is a linear combination of these two vectors. This guy here is a linear combination of these two vectors. So I can say this. I can say that where can I let me erase this and write it here. This is crucial. So I can say that the solution set of this ax equals 0, let's say ax equals 0, ax equals 0 is span of what vectors? This minus 2, 10, 1, 0, and 5, minus 12, 0, 1. Right? Span of this. You can see that this is a linear combination of these two vectors. Any solution to this equation is a linear combination of these two vectors. So the solution set, which includes every solution, is in fact span of these two vectors. Now, as span of these two vectors are in R4. So this solution set is a subspace of R4. This, let me erase this and write it here. Just let it go. So this is a subset of R4, and not just subset. This tells me that solution set is a subspace of R4. Is a subspace of R4. So, yeah, what is special here, I have a homogeneous system. In fact, it is a theorem that a solution set to a homogeneous system is in fact a subspace of R4. So let me write this as a theorem and finish this. Subspace, same section. And this is a theorem. And again, this is important. Solution set of A, let's say n by n, x n by 1 equals 0, n by 1 is a subspace of Rn, right? Is a subspace of Rn. So solution to a homogeneous system is a subspace of some Rn. And why Rn? Because you see this Xn belongs to Rn. Xn is solution. Solutions are this. And each one of them belongs to Rn. And depending on the situation, this m and n, depending on the situation and how many, say, 0 rows I will get, it becomes some subspace with certain dimension. We will see what that dimension is in the coming sections of this important and interesting chapter. Okay, so let me stop and I will discuss other things in the next lecture.